We start with defining what reinforcement learning is, how it differs from other types of learning, like supervised learning, unsupervised learning, and other types of learning techniques. But before diving into the definition and essence of reinforcement learning, let's first see the evolutionary aspects of um, technology or digital technology in general towards artificial intelligence and then towards reinforcement learning. So as you remember, we have this age called an industrial revolution age in which um, we have repeated physical solutions or automation of repeated physical solutions. So we used to entitle, or we entitled this one as an industrial revolution age or the machine age. Then we have the second one, the digital revolution age. This revolution, we automated the repetition of mental solutions in addition to physical solutions. So this is one step towards artificial intelligence, but in the artificial intelligence age, we were able to come up with machines that find solutions by themselves. So that's what we call ML or machine learning or any other learning methodologies. Deep learning, machine learning can be categorized here. So generally, these technologies, these findings describes what artificial intelligence is. But right after that, right after the invention of artificial intelligence, then we came up with this idea or this scenario in which we only provide the problem and the goal, and then the machine will learns the best way towards the goal from the initial state or from the problem state by using interaction and trial and error approach. That's what we call reinforcement learning. I will be discussing this one in detail later, okay? So this learning, by having only the problem and the goal state, requires learning autonomously or autonomous learning to make decisions. So that's why the first step of reinforcement learning is the learning itself, learning about the environment, learning about the pros and cons of the environment the agent is supposed to interact or the agent is interacting. So to this end, we do have a very preliminary or foundational paper, which is contributed by Alan Turing. This paper, this is very common paper in the realm of artificial intelligence, computer science, specifically the idea of, or the first model that like perfectly or correctly represents the human learning process or the human mind in general is depicted or stated by Alan Turing on his first publication on 1950. So in this paper, what he does was he tried to analyze the behavioral aspect of human mind or human brain, we could say. So then he said, we can assume a human brain as a white, just a white thing, like a white paper, which has only an initial state. And as the human does, it gradually accumulates information by interacting with the external environment, it accumulates information, and then gradually the initial state, that white state, that empty state will be fulfilled with a lot of experiences and their corresponding regrets or reward. So he suggested that the same approach, the human learns the environment, could be applied for the machine to learn its environment and come up with the best optimal solution or the possible optimal solution, I would say. So this is the first foundation or a benchmark a jumping spot for reinforcement learning researchers to contemplate on the possible ways of coming up with machines that learns through interaction or trial and error, as the human does. So this mapping between how human learns and how machine should learn is first proposed by Alan Turing. So now, what's artificial intelligence? From the perspective of reinforcement learning, we can define artificial intelligence or even intelligence in general as to be able to learn, to make decisions, to achieve goal. So the most important keyword here is learning. Learning, So if something is able to learn, about its environment, then we can consider it as an intelligent being or an intelligent entity. So in general, intelligence generally can be defined as learning to make decisions, and those decisions should lead you towards some goals. So here we do have learning, the most important keyword, but we are learning to make decisions, and those decisions are all about coming up with the best actions to achieve the desired goals. So that being said about intelligence and then artificial intelligence, we have defined artificial intelligence in our previous classes. For instance, we used okay. Is it question? I think yeah, Zamadkun, please. Okay. I'm recording it now, but the internet connection, it might not be your problem, your exclusive problem. So I might have the same issue. So are you listening to me? Like, is that okay? Any issue ሊሆን ይችላል ብዬ ነው። Okay, okay, I'm recording it. Okay, I'm recording it. Okay, thank you. Okay, so we just defined what intelligence is, and we already know what artificial intelligence is. So we can extend the definition of artificial intelligence from what we just defined, which is the definition of intelligence, right? So from our previous class, for instance, we defined artificial intelligence from the rational agent approach, right? We can also we also defined it as like acting like human, or acting humanly, thinking humanly, from the perspective of nativists, and then from the perspective of behaviorists, we said it's more to acting rationally and thinking rationally. So just we do have that definition for artificial intelligence, but specifically when we say intelligence, its major emphasis is on learning to make decisions to achieve the desired goal. That's one thing you should underline on. Now, what's reinforcement learning? Again, let's define reinforcement learning from the perspective of humans, okay? Because as we already said, Alan Turing is the guy who showed us the mapping between how human learns and how machines should learn, right? So reinforcement learning is inspired by this definition. So for that purpose, whenever we define reinforcement learning, it's really recommended to start from how humans learn, okay? So people and animals learn by interacting with our environment. So we do learn by interacting with our environment. So this might be different from other types of learning, like passive type of learning. The first thing, it's active. It's active learning. Because why we are saying it's active? Because a human might touch, for instance, something like some hot material, and then the reward or the regret for that action is acquired immediately. So for that purpose, it's active learning. It's active learning, a learning by interaction. And the second thing that defines reinforcement learning too is that people learn sequentially. Okay? So in this case, future interactions can depend on earlier ones. For instance, the same example could be brought up here. A human who touched like a fire, for instance, at time t, might not touch that same fire at time t plus 1, for the same purpose that the reward for the action at time t is more to negative or more to regret than positive reward. So for that purpose, these are sequential. So earlier actions determines what the next actions would be. Earlier states determines what the next states will be. Earlier actions determines what the next actions will be. So for that purpose, it's sequential. So human learn by interacting with our environment, and the type of learning, human or animal or any other entity which is intelligent, is active and sequential. And again, it's also goal directed. So it's better to relate what we are talking about here to the definition of intelligence here: learning, making decision, and achieving goals. So one of the important things about human or people learning is that people can learn without examples of optimal behavior. That means people can learn by interacting with the environment and then analyzing the result. analyzing the reward or the regret that's the result of your previous action or human's previous action. So in that case, it's not necessary to have an example of an optimal behavior. For instance, a type of learning that has an example of an optimal behavior is called supervised learning, right? It's supervised learning. So, but in case of reinforcement learning, or in case of the real learning, which is reinforcement learning, human learning, you do not necessarily should have examples of an optimal behavior. We do have a goal, but it doesn't mean a path towards the goal, but the goal. So as an agent, you will not know where the goal is. We have seen this one in the model-based execution of solution, like we call it searching, right? During the searching phase, we do not know like where the goal is, but we might know how far we are from the goal at each stage. So the same thing is true here. In the case of reinforcement learning or relearning or pupil learning, there is no necessity to provide example of optimal behavior. That's one of the characteristics of reinforcement learning too. Then instead, we optimize some reward signals based on our interaction. So this basically defines what reinforcement learning is. So here we can define reinforcement learning. The first thing, it's learning by interaction with the environment. It's active learning and sequential learning. And again, it's goal-directed learning. And it's a learning without example. It's a learning with the principle of reward hypothesis. This concept is called reward hypothesis. It's a learning based on reward hypothesis. That means you simply define a good action by the reward you get after that, by the corresponding reward you get for each of those actions. So in this case, we define reinforcement learning as learning by interaction, and you are supposed to interact with the environment, get some reward and observation, and based on those rewards, whenever the value of the reward is good, then you excel more on your previous approach that gave you the reward that you have now. If the reward is bad, then on the contrary, you have to adjust something against the approach that you used at that moment or at time t -1. So it's reward-based hypothesis. So just pictorially describing this interaction loop, we do have an agent. We said an agent or a rational agent is an agent that does something right? In our previous course, we defined this one. So an agent is supposed to interact with the environment. So interaction is described by its action, by the way. So an agent will issue some kind of action to the environment. This environment doesn't mean the world, necessarily. Like it's not, the verbatim is not the world or the earth. When we say the world or the environment, it might mean the chessboard, for instance. It might mean a grid world. It might mean some kind of gaming environment, or it might mean the traveling Romania problem or traveling Ethiopia problem. Okay, so we do have the environment, we do have agent. So in between this, we have the principle of reinforcement learning, in which the agent issues action to the environment and observes the change of state. And this change of state comes along with corresponding rewards. So an agent issues some action, observes the environment. If the environment and its corresponding reward is negative, then the agent will apply another action to some extent different from the action it issued before, with the aim of acquiring better reward and better observation. So this is generally the reinforcement learning loop or the interaction loop. Okay, so the goal of this interaction loop is basically to optimize sum of rewards through repeated interaction. So whenever we say repeated interaction, we are referring to a trial and error approach. Okay, so for instance, agent might be somewhere here. The agent might be somewhere here. The goal might be somewhere at the top right corner of this plane. Then in between this, there are many possible actions and many possible states in your state space graph. That means the state space graph is the world. Then the agent learns by issuing one, say for the first round, one random action and it, given its proximity at time t, and compared to its proximity to the goal state at time t -1, then this is a positive reward. Okay, then like that, it will apply all possible actions aiming to reach to the goal state optimally. Then the one with best or larger cumulative rewards or sum of rewards is acquired, or the list of actions with the best cumulative reward is acquired or collected as a constituent of the best path towards the optimal solution. So I think this concept in our previous class, in the AI principles and techniques class, like in that class we have been learning about this process, the whole process, and from the perspective of reinforcement learning, that is part of the reinforcement learning. The first part of the reinforcement learning, we call it learning. So in order to learn, one of the approaches would be, for instance, model-based learning. We call it searching. So as I already mentioned, reinforcement learning is learning based on reward hypothesis. That means in the case of reward hypothesis, any goal can be formalized as the outcome of maximizing a cumulative reward. So a cumulative reward is list of rewards, or the sum of rewards you get after applying consecutive actions on the consecutive states of the environment. And the agent is responsible to do that. So reinforcement learning is based on reward hypothesis. So the goal is defined by or formalized as the outcome of maximizing a cumulative reward. So here, the most important aspect is, the concept of cumulative reward. For instance, let's say we have this linear path to reach to the goal state. Okay, say we do have the initial state, and somewhere here we do have the goal state. And this agent might use 2 or 3 optimal paths to reach to the goal state, and at the same time it might use other suboptimal paths to reach to the goal state. So the suitability or the optimality of a given action cannot be determined by itself, but by its cumulative impact. That means an action A that takes you from here to here does not necessarily describe how good it is, but its synergy with other actions and its synergy that provides the best path towards the goal state is the main key point to describe how good it is in this environment. So when we say cumulative reward, we are not talking about immediate reward. So for instance, if you are a greedy agent, you might focus more on immediate rewards, right? So for instance, you remember this greedy algorithm, right? The greedy algorithm always takes the best backward cost or actual cost, and it might end up looping somewhere, right? From our previous class. So the same is true here. To avoid such kind of problems, we came up with the concept of cumulative reward. That means from all paths that leads you from the initial state to the goal state, the one with better cumulative reward is the optimal path. So there is no way to define an action by itself, but with the consequence or with the sequence of states and their corresponding cumulative rewards defines how good action is and how bad this action is. So just to give you an example about reinforcement learning problem, just before diving a little bit more on this aspect, let's now differentiate between different types of learning mechanisms. For instance, I think on Saturday, I think Mabratu raised this question: what's the difference between supervised learning and unsupervised learning? Reinforcement learning. What's the difference between unsupervised learning and what's that other one? Reinforcement learning. So the main difference, whenever you deal with supervised learning, you do have an example of the optimal behavior, right? An example of the correct answer. But in case of reinforcement learning, you do not have that one. The second thing, in the case of unsupervised learning, you will not have an example of the best behavior, which makes it similar to the reinforcement learning. But the purpose of unsupervised learning is simply to mine patterns and to perform some kind of clustering based on those pattern similarities or by matching those patterns. But when you come to reinforcement learning, the purpose of reinforcement learning is not to build or to come up with some kind of clusters, but it's to learn the best path towards the solution by trial and error approach. Okay, we do have the goal state. We know what we know when we reach to the goal state in the case of reinforcement learning. But until we reach to the goal state, our main purpose is to come up with, you know, the possible list of actions that leads you one step toward the goal state every time. So this is the major difference between supervised learning, unsupervised learning, and reinforcement learning. So usually reinforcement learning is a problem-solving mechanism. Whenever you have a problem which is characterized by sequence, for instance, adversarial games could be characterized by this kind of sequence. Other types of game could be characterized by alternating sequences. So for that kind of problems, we could use reinforcement learning problems. So that being said about what distinguishes reinforcement learning from other types of learning, like supervised learning and unsupervised learning. Now let's see some of the examples of reinforcement learning problems. The first one, flying a helicopter. So managing an investment portfolio, control a power station, make a robot work, play video on board games. We can consider this as reinforcement learning problems as long as they have reward and corresponding regret. So any problem that needs interaction with the target and provides or requires you to be guided by the corresponding rewards or the output rewards and regrets can be considered as reinforcement learning problem. So in this context, we do have a fly helicopter, for instance, fly helicopter problem. We can say it's a reinforcement learning problem because it does have reward. Like we can consider airtime as a reward, inverse distance as a reward. In the case of, for instance, making a robot walk or make a robot walk, the reward could be distance or it could be speed, okay? So if the goal is to learn via interaction, so these are all reinforcement learning problems. If you have to interact with the environment and if you have to guide your consecutive actions or subsequent actions based on the reward you get from your previous action, then such kind of problems can be generally described as reinforcement learning problems. So there are distinct reasons to learn in general. The first reason to learn is to find solutions, right? To move from some state to the goal state, to find solution, to come up with a solution for a given problem. So that's the first reason to learn. So in this regard, for instance, supervised learning solves this problem. Supervised learning solves this problem. So finding a solution. For instance, a program that plays chess really well could be achieving one type of solution or one sort of solution. A manufacturing robot, for instance, with some kind of item relocation could be considered as, you know, an agent that learns, that means intelligent agent that does this kind of operation. But the most important part, which is the second part of the second reason of learning, is adaptation. And this adaptation is online adaptation. It's not offline adaptation. For instance, in the case of supervised learning, it's rather offline adaptation than online adaptation. You do not have to interact with the real environment, but you have to interact with a model of some presumed real environment that might not be really representative of the environment. So in such kind of cases, we even tend to face with overfitting problems, right? Whenever the data set doesn't align with the real environment. So the two reasons of reinforcement learning is the first one, solution, finding solution, and the second one is adaptation, but specifically online adaptation. This online adaptation is the ability to deal with unforeseen circumstances. So we might classify this one, or we might label this one as the capability or the capacity to generalize, or we usually call it generalizability of a given machine, the capacity of a given model, I would say. But this is even beyond generalizability. For instance, if we were talking about adapting offline, then generalizability strictly describes this one because, in the case of generalizability, for instance, in any deep learning or machine learning algorithms, we first train our model using predefined independent and dependent variables. Then after that, we test our model in unforeseen circumstances. But whenever you see defects with your model, in that unforeseen circumstances, you do not update it online. So in that case, we can say, okay, we are not updating our model online. So with that, given that scenario, then our model's generalizability capacity is this percent in case of ROC or AUC or any other metrics. But in the case of this adapting online, we are not talking about that kind of generalizability, but we are talking about continuous learning mechanisms, or being able to continuously learn efficiently and in real time or online by interacting with the environment. So most of the learning algorithms, they satisfy the first reason or the first essence of learning, which is finding solution. But the most important essence of learning is adapting online, or having the capacity to learn online from the real environment. For instance, look, assume a child. For instance, assume a child who doesn't know anything about this world. So his parents might not have told him anything about this world. He might confront with, say, a cat, for instance, a naughty cat, let's say. Then for the first interaction, that cat might bite this guy or this little kid. So in the second incident, it might again bite this kid. As this process goes on and on, this intelligent agent will learn from those previous situations or circumstances. So so the conclusion from this would be, whenever I confront this cat, she will bite me back, or she will bite me. So this is a negative reward. So for the next time, whenever he sees or she sees such kind of things, this child will cry or will do something to go away from that cat or that entity, right? That's the nature of human being, or that is the nature of, in general, an intelligent entity. So the same thing should be modeled in artificial intelligence, and that can only be modeled by using reinforcement learning. This second aspect can only be modeled using reinforcement learning, because in this case, we are allowing our machine to learn from interaction in real time. That means online, during operation. Okay, so it's better to see reinforcement learning's unique features from these two perspectives. We can now formalize the definition of reinforcement learning. So reinforcement learning is a science and framework of learning to make decisions from interactions. So this requires time, consequences of action. This consequence of action might not be immediate consequence of action, or we call it reward. It might be cumulative consequence of action or long-term consequence of action. Actively gathering experience, we call it accumulating observations or history. Predicting the future, once you have a model to resemble or to represent the environment so far you have interacted, you should be able to, or that intelligent agent should be able to predict from what it has, So this step is called prediction. So one of the techniques for prediction is searching, by the way, because in the model environment, in an abstract environment, we tend to come up with possible solutions. So we call it prediction. So prediction is the first major problem of reinforcement learning. The second major problem of reinforcement learning is control. So whenever we talk about learning to make decisions by interaction, we need to think about time. Second, consequence of actions. Third, observation or actively gathering experience. Fourth, after gathering experience, we will build a model, and by using that model, we have to predict the future. And then we have to deal with stochastic or probabilistic nature of the dynamic world. So these things should be considered whenever we deal with learning to make decisions by interaction, or whenever we deal with reinforcement learning. So reinforcement learning is a true formalization of the AI problem. So this reinforcement learning, for instance, supervised learning is not a true formalization of AI problem, because supervised learning might allow you to find solution and to adapt online, but it doesn't allow you to adapt offline, but it doesn't allow you to adapt online, right? So for that purpose, reinforcement learning is considered as a true formalization of the artificial intelligence problem. The main reason we say this is, AI, the inspiration of AI, or AI aspires to be a cognitive agent, right? an AI agent aspires to be a cognitive agent. And among the most cognitive agents in this world, the first target of AI is human being. So for that purpose, AI achieves its desired goals whenever it completely resembles human being. One of the mechanisms to resemble human being is by achieving these two requirements. The first one, by finding solutions. Second one, by adapting online. Those other algorithms can find solutions, can generalize good, but they might not adapt online. But algorithms or machines, which are empowered by reinforcement learning, can adapt online. So for that purpose, we call reinforcement learning is a true formalization of an AI problem. I suggest you to read this paper, an early paper, which is Playing Atari with Deep Reinforcement Learning. Atari is a game in which you do not know the rule of the game when you join it for the first time. But through interaction, you tend to learn how this Atari game works and start playing along with it. So this is a true example or a true living testimony of how the agent or an intelligent agent interacts with the world and then finally learns the substrates of this world and then go hand in hand with its rules and requirements. So Atari, I think this is a game. It's online game. You can find it now. Check it out. Like when you start playing that game, it doesn't have any specified rule. You have to do something and see how it responds. Then from there, you tend to learn the characteristics of that game and then play per session level. Now let's formalize the reinforcement learning problem. Whenever we say formalization, we are referring to the mathematical description of the problem itself for reinforcement learning. So we say reinforcement learning is learning by interaction. An agent interacts with the environment and the environment provides some kind of observation and reward. And after noticing those rewards, the agent then shapes its action using some kind of policy. So here we can define this phenomena from two perspectives. One, from the agent perspective, and two, from the environment perspective. By the way, from the previous course, you can consider the agent state as a search tree and the environment state as a state space graph. Okay, this would be easy for you. So at each step t, or at each time t, the agent receives observation t and reward rt, observation ot and reward rt. We do have agent, we do have action before, so for that action, we observe the state of the environment at time t and then the corresponding reward rt, always when we start interacting with the environment. Then, after observing the state of the partial state, usually this is a partial state, okay? After observing the partial state of the environment and its corresponding reward, then we come up with a policy that generates this action. And we issue this action to the environment. That is what the agent does at time t. Then, on the other hand, the environment receives this action at time t, which is issued by the agent, and emits another observation which will be considered as the state of that environment as a consequence of the action issued by the agent at time t. So we call it OT plus 1, O at t plus 1, and it's called by trial and error. We have observation at the first time and corresponding reward, and for every observation and corresponding reward, there will be a policy to drive what? Action at time t. And this action at time t produces observation at time t plus 1 and reward at time t plus 1. This cycle goes on and on, by the way. So, for instance, at OT, the agent might perceive the environment or the state of the environment at time t plus 1 and rt plus 1 and issues A at t plus 1. And then the corresponding observation will be O at t plus 2 and R at t plus 2. So this is the preliminary constituents of the reinforcement learning environment. So we have been talking about rewards, right? So now let's talk about what reward is. So the first thing, reward is scalar. So there is no such thing as a bad reward or a good reward. There is, either a small reward or a large reward. So the complement for this one would be regret. So I usually like to say negative reward, but whenever I say negative reward, I meant regret. Okay, regret. So a reward at time t is a scalar feedback signal. That means whenever we say it's a scalar, it does have a magnitude, but it doesn't have a direction, right? So there is no such thing as negative and positive, but it's a signal, a feedback for your previous action. For instance, RT is a signal for your previous action AT minus 1. So this reward indicates how well the agent is doing at step T. Okay. For instance, if RT is, for instance, minus 1 or RT is 1, let's say, then this means it's a description of how an agent is doing at that moment, at time T. But it's a consequence of the previous action A at T minus 1 and the previous state of the world S at T minus 1. Okay, so the overall goal of this reinforcement learning agent is to maximize the cumulative reward. What does it mean? We already said the process is a trial and error process. That means there is a repetition. We tend to learn as a reinforcement learning agent. We tend to learn by repeating actions and observing the environment, and then on top of those observed environments, we have to apply another action like that repeatedly. So for that purpose, the overall goal of a reinforcement learning agent is to maximize the cumulative reward. What do we mean? The cumulative reward is the reward from the initial state, or the reward for the very first action, and for the on top of the very first state of an environment, to the very last action in the very last state of the environment, whenever we exit searching, or whenever we stop looking for the solution, or whenever we acquire the solution. So we represent this one as a return, or we call it G at time t, capital G at time t. So capital G at time t is the sum of all rewards from R at time t plus 1, because for every action at time t, you get reward at time t plus 1, right? So you cannot issue an action at time t and get its corresponding result at time t, but the assumption is you issue action at time t and you get observations and rewards at time t plus 1 on the next time. So this does not mean necessarily the unit doesn't mean necessarily it's a second or some kind of minute, but the resolution is based on the action and response manner. So for every action at time t, the second alternator will give you rewards at time t plus 1. Okay, so this sequence of rewards for every sequence of action on top of every sequence of states is called return. So we already said reinforcement learning is based on reward hypothesis. That means we define the reinforcement learning problem, or we formalize it as the outcome of maximizing GT, or the return, or the cumulative reward. The second thing we need to discuss about is the value of state. You are familiar with this term, value of state. We have been doing so many calculations to get the value of state of an agent, or a state actually. So we call the expected cumulative reward. This GT is called value of state, or value. That means GT is basically the value of that state at time t. Okay, the value of that state at time t, or it's simply the contribution of the current state the agent produced for the final goal state. We call it value of state. So value of state is the result of the expected function. The expected function, sometimes we call the expected function is a Bellman function. I'll discuss about that one later. But the value of state is computed as the cumulative reward, or the return, given the current state S, or the current state S at time t minus. Okay, value of state is expected cumulative reward. Mind you, it's expected cumulative reward. We are talking about prediction given some state at time t. Some state of what? Some state of the world as perceived by the agent. So we call it the agent state. The agent state, or we can also call it observation at time t. So this value, the value of state, depends on the action the agent takes, right? We already discussed about this one here, because this agent issues this action. Are you with me, by the way? So we already said ምን ብለናል? እዚህ ጋር ያለው አክሽን ፕሮዲውስ የሚያደርገው ሪዋርድ አት ቲ ፕላስ ዋን ነው ኖቲስ የሚደረገው ወይም ኦብዘርቭ የሚደረገው ብለናል። ራይት ኦብዘርቭ የሚደረገው ያኔ ነው ብለናል። ስለዚህ እዚህ ጋር ስንመጣ value of state ምን ላይ ዲፔንድ ያደርጋል አለ? the value depends on the action the agent takes. action the agent take የወሰደው የትኛው ነው? በዚህ ኬስ ኤቲ ላይ ነው። ኦኬ value of state ዲፋይን የሚደረገው የቱ ጋር ነው? በሪዋርድ ነው፣ በኩሙሌቲቭ ሪዋርድ ነው ብለናል። ስለዚህ ኢሚዲየት ሪዋርድ ፕላስ ከዚህ በፊት የነበሩት ሪዋርዶች ኩሙሌቲቭሊ አንድ ላይ የምንወስዳቸው ከሆነ ሪተርን ይባላል ወይም ኩሙሌቲቭ ሪዋርድ ይባላሉ ወይም በሌላ ቋንቋ ምን ይባላሉ እያለን ነው። ሶ value of state ቅድም ካብራራ ነው ጋር ስናነጻጽረው value of state is return no basically given what some state it's return, it's expected return, it's expected cumulative reward given some state at time t at the moment ማለት ነው። and we can further substitute this return with its sequentially applied actions. Then we can say value of state is the expected sum of rewards given state of the agent at time t or given the current state ማለት እንችላለን ማለት። So as we already mentioned, the goal is to maximize the value of state or the value of this state. Okay, so here what we do is we usually change the actions and see which actions provides us the best value of state. Okay, that's what we call trial and error approach. So rewards and values defines utility. You are very familiar about the word utility. So rewards and values define utility of states and actions. Okay, so since there is no supervised feedback, we tend to usually guide our navigation through the utility of the state or the value of state and the value of action. So whenever we focus more on the utility of states, we call it value of state. Whenever we focus on the utility of action, we call it action value based technique. Or from the first class of this course, from the first course overview session of this course, we defined reinforcement learning problems into three. The first one, or a mechanism to solve reinforcement learning problems into three. The first one, value iteration mechanisms, which is utility of state-based mechanism. Then policy iteration-based mechanism, which is action value-based mechanism. And the third one was action critic mechanism, which considers both utility of state and utility of action, depending on the situation. So we can define this, the value of state, recursively. So we can say the return gt at time g at time t, or the return at time t, is equal to immediate reward, which is rt plus 1 plus gt plus 1. So this is simply this with time t plus 1. So this will lead you to calculate rt plus 2 plus gt plus 2, right? So this is recursive function. So this can be rewritten as value of state is equal to the expected immediate reward plus value of state at time t plus 1 given the current state of the agent. So this again gradually leads us to the Bellman equation, which is the same as this value of state equation, but with one different operand, which we call it discount factor. I will talk about what discount factor is, why we need discount factors in the next consecutive slides. So we said the goal of reinforcement learning and this trial and error approach or repeated execution approach is to maximize the value of state by taking the best actions which we learn from repetitive procedures. Okay, so as I already said, the goal of this reinforcement learning is to select actions to maximize the value of states. Okay, but actions have long-term consequences, and again rewards may be delayed. What does it mean? We might be applying, let me go back here. The agent at time t might be applying action at t. Say this action at t is called A. Then the first scenario plus n being some number, above 1. So since there is such kind of problem, reinforcement learning problem is not generally, or basically issuing some action to the environment, observing the immediate reward, and then fine-tuning your actions and issuing it again. No, it's not. It's mainly based on long-term rewards rather than immediate rewards. So that's why we said it's a process of selecting actions to maximize value, but this process of selecting action is mainly guided by long-term consequences or long-term or cumulative rewards rather than immediate rewards. So just for your information, this RT plus 1, we usually call it immediate reward, but all other rewards after this are called long-term rewards. So the summation of these long-term rewards could be referred to as cumulative reward. Okay? So let's see the necessity of considering long-term consequences or rewards rather than immediate rewards. Okay, sometimes you may have to sacrifice immediate rewards to gain more long-term rewards. Let's reconsider the reinforcement learning problem which we discussed a couple of minutes ago. Refueling a helicopter, for instance. Refueling a helicopter. So I think if it is near, I can go back to it. Look, we do have a fly helicopter, a reinforcement learning problem, and we identified L time as a reward. Then assume we are flying a helicopter, and then all of a sudden we see the fuel gauge is down. So we have, say, only 1 kilometer to go. We have to land immediately. So from this reward perspective, for instance, you might say, I have to fly, right? Because the best way to reach to your goal is by continuing the flying process, right? Not by parking somewhere or landing somewhere and refueling your fuel tank. But considering the long-term consequence of this incident will let you have the wisdom to know that the helicopter will crash unless you refuel it within a specific period of time, right? So for that purpose, reinforcement learning is not all about observing the immediate reward, but it's also all about observing cumulative rewards or long-term consequences. Is it clear? Okay, so the refueling helicopter case is one scenario. For instance, defensive moves in a game, for instance. Have you seen such kind of guys? I'm most of the time defensive, like while playing adversarial games, because the chance of winning later may enhance or may increase if you are very protective and defensive of your realm or your arena, So these are one approach, for instance. Learning a new skill, for instance, can be costly, and even though it's time consuming at first. It's costly and time consuming at first, but by learning new skill in the long term, you will have some kind of thing. So that's what you are doing right now, right? So that being said about the value of state, now let's talk about one other important concept, which is called policy. A policy basically is a mapping from states to actions. A mapping from some state to action is called a policy. So far we have discussed about the value of state. We said value of state is defined as a cumulative reward or return. Okay? That means that cumulative reward can only be acquired whenever the agent repeatedly interacts with the environment and accumulates its observation and corresponding rewards. So for the agent to take some action, it should have some kind of policy. Because policy is a mapping or an agent or an entity or a function that produces actions based on the current state of the agent. So we can also evaluate, or you can also compute how good our actions are in addition to how good the state of an agent is in relation to the goal state. So this can be done by calculating the value of actions rather than the value of the state. So in the previous session, we have been talking about the value of state. This is basically the value or the contribution of this state S at time t for the overall cumulative reward, okay? Or for the fact that how far it is from the goal state. But when we come to action values, this is basically the value of the contribution of, or the value of the contribution of the action for the overall proximity of the agent state to the goal state. Okay, so we represent it as using the Q function. If you hear, for instance, Q learning, deep Q learning, deep Q based reinforcement learning, deep Q reinforcement learning, it's mainly based on action values. So we use Q function to represent or to calculate the value of an action at time t. So it's more or less the same as the value of state, but the perspective is different from the value of state. Here, our perception is mainly directed to the action, not the values, or the states, or not the state, the value of the state, but the value of the action the agent is taking at time t. So the value of an action given the state of an agent S is computed or calculated as the expected return given the current state S and the current action A. Look, there in the previous one, the value of state is what? The cumulative reward or return given the current state. Here we are only considering what? We are only considering the current state of an agent. But here we are considering both the current state of an agent and the action being taken, which will result in the observation at O at t plus 1 and reward R at t plus 1. So action value SA, that means the value of action A given the state S, is calculated as cumulative reward given the current state and the current action being taken. This can further be expanded as follows, because GT is RT plus 1 plus RT plus 2 plus RT plus 3, like that. So we'll take like details of this in our consecutive chapters. Okay. Now let's talk about the core concepts of reinforcement learning from the formalism perspective. So one way or the other, we have been talking about the environment, because the agent interacts with the environment. The environment is mainly characterized by dynamic nature, or the nature of the environment is dynamic. That means whenever you apply action, it will change its state, or the part of that environment visible to the agent will change somewhat. So it is a main characteristics of dynamic entity. So the environment is dynamic. The second one, the reward signal. The reward signal, the better reward signal you have, the good proximity you have against the goal state. And again, the other core concept here is the agent. The agent in itself contains the agent state. This is either the complete state of the world or the partial state of the world. We do have under agent state a policy. A policy is a function for the agent to produce action. We do have value function estimate. We'll talk about this function estimators in the, I think in the 6th or 7th chapter of this course. But value function estimate, that means without directly interacting with the environment, you tend to calculate the value of state of a given action in a long-term manner. You know, like you might have an immediate reward, but for all those consecutive rewards, you will execute your value of state function in a simulated world or in a such type of mechanism. And the other one, we do have model. A model is an abstraction of the environment. That means it's what you build, predict what will happen whenever some kind of action is issued to the environment. So without actually executing that action on the real environment. Okay. Now let's talk about the agent in detail. So we said that among the components of the agent, we do have the agent state. The agent state is usually a partial state. Okay. We do have an observation. at time t, for instance, we have state of the agent. We are talking about this state of the agent. From this state of the agent, we will use a model to predict the next state. That's one thing. We will use policy as a function to come up with an action that will lead you to the next action. So at time, with this action and with this prediction model, you will have another state of an agent at time t plus 1, which is, so in relation to this one, we are specifically talking about the agent state, but there is also an environment state. The environment state is an exhaustive list of states, or from the previous class, for instance, an environment state is the state space graph. That means it's a state in which all possible states are represented, all possible actions are represented. So usually this environment state is not visible to the agent, and most of the time the totality or the entirety of this environment state is not relevant to the agent. So here we need to come up with a mechanism to extract the relevant portions of this exhaustive list of states or the environment state. So we'll talk about that one. But whenever we say agent state, it doesn't necessarily mean the environment state. It usually means the subset of the environment state which is visible to the agent. But in some conditions, again, the environment state might be the same as the agent state. Okay? Might be the same as the agent state. For instance, if the environment is small enough to be perceived by the agent at one time or through sequential manners. So the agent state usually is defined as a history generally. And this history is a sequence or a full sequence of observations, actions, and rewards. So observation at time, say, 0, action at time 0, and its corresponding reward and observation. And again, the same thing continues like this. So this is one action. Like we do have observation, and then based on this observation, we come up with an action, the next observation, and the next reward. So for all consecutive actions, we will have consecutive observation and reward, consecutive observation and reward. And for every reward and observation, we will have a corresponding policy that generates action for the next observation and the next reward. So this log is represented as history, and this history is representative of the agent state in general. So whenever we say agent state, we are not talking about the immediate state of the agent. That means we are not saying the agent is, watching or like interacting with this state of the environment. We are generally saying the agent knows this much about the environment through its previous interactions. Okay, so history defines what agent state is in general. Okay, so for instance, assume a sensory motor stream of a robot. A sensory motor stream of a robot. So if you know a sensory motor, for instance, if you take right hand of a humanoid robot, it might have at least 3 degrees of freedoms, or 3 joints, right? 3 joints. So those 3 joints, for instance, whenever the robot tries to move from bottom position to whenever it tries to move its hand from bottom position to the top position in its jurisdiction in general, then the degree of freedom, the 3 degrees of freedoms will have sequentially different values over time, right? So you can consider this history as an agent that stores or that logs the sequential value of those 3 degrees of freedoms over time. Okay, if you are familiar with robotics. So this history basically is used to construct the agent state ST. One more important thing here is fully observable environments. An environment is fully observable if the observation of an agent at time t is the same as the agent state and it's the same as the environment state. So እነዚህ ሶስቱ እኩል ከሆኑ then we call it fully observable environment ነው እንላለን ማለት ነው። So ST basically is what? ST የምንለው history ነው ብለናል። history over the time and agent accumulate ያደረገው knowledge ነው ስለ environment. OT ደግሞ on top of that ያለው የኤጀንቱ perception observation ነው, whether it is accumulated or not. If these two are the same as the environment state, then the environment is called fully observable environment ይባላል. ግን most of the time there is no such thing as fully observable environment, because we are assumed to interact with a complex world, a dynamic world, and usually this complex world or dynamic world is not fully observable. So for that purpose, we come up with this useful mathematical framework. We call it a Markov decision process. So a Markov decision process is there to avoid the necessity of having fully observable environment to come up with an optimal solution whenever you deal with it by interaction. So according to Markov decision process, a given environment is a Markov environment. A given environment is a Markov environment, or a given decision, even not from the environment perspective, but from the decision perspective. A given decision process is a Markov process if the reward and the state of an agent after applying some action at time t minus 1 and being on a state st minus 1, given the current state st and the current action at is the same as the reward and state you get even after having the complete history of the environment, or the full observation of the environment and the full list of actions at time t. ምን ማለት ነው ይሄ? A decision process is Markov ምንለው መቼ ነው? reward እና corresponding state ከማጋ እኩል ከሆነ ነው። as if full observation ኖሮት full list of actions ኖሮት ከነዛ ውስጥ መርጦ ቤስት የተባለውን አክሽን አፕላይ አድርጎ ከሚያገኘው ሪዋርድ እና ኮረስፖንዲንግ ስቴት ጋር ፕሮባቢሊቲው ተመሳሳይ ከሆነ the probability of r ሪዋርድ ማለት ነው and s given s at time t and a at time t is equal to the probability of r and s given the history at time t and list of actions at time t, then we call this decision process Markov decision process ነው እንላለን. We call the environment Markovian environment ነው እንላለን ማለት ነው. Okay? For instance, if you have the full history here, that means if ST is equal to OT is equal to environment state, the decision you are going to take is a Markov decision. True. The environment is a Markovian environment, but it's large, so it might even be growing indefinitely. So this kind of representation is not required. So for a given environment to be Markov, to be in Markov conformance, it should be the first thing. The exhaustive approach would be it should be the agent state should be the environment state. So HT should be ST, but this is not usually recommended because it's not usually possible. And even if you can represent the HT in memory, then it might gradually keep growing, and that will not allow you to compute for all consecutive rewards and states. Okay, so the full environment and agent state is Markov, but it's large. Even if you take the HT, which is the total history of the environment representing the whole environment state, but at time t, that means it's not at time t plus n, it's yet to grow. So for that purpose, since it keeps growing, it's not recommended. So for that purpose, the idea here is that in reinforcement learning, you have to come up with this function. We call it update function. We call it expected function, actually, usually, that gives you a reward and a state given some current state and list of actions, as if you got them from an environment to which you have a complete vision or a complete understanding of, and from the sequence of observation, action, reward perspective, and also from the perspective of all possible list of actions. Yeah. So we use ST to denote the agent state, and I already said this one, not the environment state. There are also partially observable environments which cannot be fully seen by the agent. So for that, we do have this decision process called partially observable Markov decision process. We'll talk about this one in our next class. Actually, we'll have a separate Markov decision process chapter. There we'll dive more into these aspects. But the bottom line, like the main important thing here, is that the agent state is different from the environment state. And as a reinforcement learning agent, you should be able to come up with optimal solutions from the agent state, which is most of the time a partial state, a partial view of the environment, but with a reward which is tantamount to the reward you get after having the complete view of the environment. And for that, we do have a mathematical framework. We call it the Markov decision process ማለት ነው።